In this video lecture, we'll introduce some analysis tools that are used to solve fluid dynamics problems. First, we'll introduce the notion of control mass, which we kind of alluded to in an earlier video as well. So control mass is typically used for a closed system. What do I mean by that? So I can have an arbitrary shaped object over here. It's got a mass m sitting inside it. And this is the fixed identifiable piece of mass. That's what it defines a control mass. And we'll typically use the symbol Cm for a control mass. And the edge of the control mass, or the surface of the control mass, we'll call that Cs and refer to that as a controlled surface. The control mass can interact with the surroundings, so that's important. And the way it might interact with the surroundings is in the form of energy transfer in the form of heat transfer Q or work transfer W. And likewise, you could have energy transfer in the form of heat transfer and work transfer going out of the control mass, right? So in other words, a control mass could be doing some useful work on the surrounding or dumping some energy in the form of heat to the surroundings, right? However, the question to ask is, does a control mass allow for m in and m out? And the answer is no, because by definition, a control mass does not allow for mass exchange with the surroundings. So that is definitely not possible. All right, so that's the definition, a formal definition of a control mass. The control mass can move and change shape, and you could have a different shape as shown with this red outline at a later point in time. Now let's introduce a control volume. Control volume is typically for an open system. And so the control volume, so here I have an arbitrary shaped region. I call that the control volume. The edge of the control volume, we'll also use the same symbol, Cs, for the control surface. The control volume can also interact with the surroundings in a variety of ways. You could have heat and work in. You can have energy exchange in the form of heat and work out of the control volume. Likewise, unlike a control mass, you can also have mass coming in as well as mass leaving the control volume, right? By definition, a control volume in general could accommodate for mass coming in and out, right? Typically, it could be a fluid coming in and fluid leaving my system. And the control volume might be, for instance, I might be analyzing a gas turbine system or a combustion chamber system in an application. The control volume could also move with time. So the control volume could occupy a different location in space at a different point in time, shown by the red line. And yet at another time, it can also change shape and occupy a shape as shown in the figure. All right, and so these two concepts, control mass and control volume, come in very handy. We want to separate them from the notion of what are called basic principles. And what do we mean by basic principles? Basic principles, sometimes they may be referred to as laws. I refer to them as basic principles. I think of laws as something that humans might create and make and enact. So whereas these are basic physical principles. So conservation of mass, conservation of energy, COE, Newton's second law, and then the second law of thermodynamics are examples of basic principles. There's also an angular momentum equation, which is probably not something that we will examine in great detail in this course. We will have occasion to use conservation of mass, conservation of energy, Newton's second law quite extensively in this course. If you take a class in thermodynamics, you'll probably focus on the second law of thermodynamics in addition. And typically, the statement is not absolutely true. Typically, the control these basic principles like conservation of mass or conservation of energy are written for control mass and not for control volumes. They can be written for control volumes, but you need to kind of extend that, and that's the purpose of this lecture. Now let's look at basic principles applied to a control mass. And the easiest way to think about that is, let's imagine a control mass labeled Cm as I've shown here. There are many ways you can write down conservation of mass statement. So m might be the mass sitting inside my control mass. And the easiest way to think about a control of mass statement is m is a constant, right? It doesn't change ever because the control mass interacts with the surroundings. It might exchange energy, but it doesn't exchange mass, so the mass continues to stay constant. Another way of saying this is the rate of change of mass equals 0, right? So if m were a constant, clearly the derivative of m with respect to t would be 0. So another way of saying that. So now this is probably sort of a rudimentary way to think about it. If you have a little bit of calculus now, you can start thinking about it in this manner. Can we do better than that? Can we do a little bit more detail than that, right? Another way to think about this mass is I can think of this mass as the total integral of rho dV. What do I mean by that? So I identify a small piece of volume. Let's call that little dV. And let's imagine the density at that location is rho. I multiply the two. That gives me the volume multiplied by the density gives me the mass, dm, if you will. I add all these dm pieces. Another way of doing that from a calculus language is integrating. So if I integrate over the control mass volume, what this indicates. And I use this kind of a V to indicate it's a volume. And that's what I perform that integration over. This is another statement for conservation of mass, right? So either this form or this form. This form might be relevant if the density is changing at different locations inside my control mass, and that's important. And those are applications that we'll come up with. Let's look at Newton's second law. Newton's second law basically is another way of saying F equals ma. And here I'm kind of saying F equals ma, except I got the F sitting on the right-hand side, or not the left-hand side. And I think of this as the net force acting on a system over here. And on the left-hand side, instead of thinking of that as ma, I'm going to write that as the rate of change of momentum, ddt of m, right? And typically, we need to have an inertial coordinate system, x, y, z, attached to the ground, typically in many of our analysis, or a stationary reference frame, or maybe a reference frame that's moving at a constant speed. Those might be considered inertial reference frames, right? And again, this is sort of the most basic way of writing it. I can write this in a more sophisticated way. I leave the right-hand side as it is. Now I can think of the momentum going back to this figure over here, where I had this piece of mass dm. This piece of mass dm, could I have a velocity v measured with respect to this inertial reference frame? So rho dv gives me the mass dm, multiplied by the velocity gives me the momentum of that little piece of mass. And then this momentum is a vector quantity, so that's why it's got an arrow on top. And then if I integrate this over my entire control mass volume, that gives me the total momentum, which is the uppercase M that I have in this equation, right? So another way of writing this equation, when velocity may be changing or the density may be changing at different locations inside my control mass, this form of Newton's second law comes in handy. V is the velocity, again, in the above reference frame, right? So rho dV is the mass, multiply that by the velocity, gives me the momentum. Now let's focus on the right-hand side. The right-hand side, the net forces can be written in terms of two kinds of forces, what are called surface forces and what are called body forces. Body forces, by definition, typically we have a symbol FB vector with a triple prime, and the triple prime indicates it has units of force per unit volume. And then I multiply that by the volume, gives me a force, and I integrate that, gives me the total force. So this is a volume integral. Similar idea, notice this has a double prime associated with it. So this one has units of force per unit area, and the area is along the surface of this control mass surface. And then if I take this Fs double prime, force per unit area, multiplied by the area dA on that surface, and integrate all of those, I'm going to get the total surface force. So the right-hand side is made up of two pieces, the surface force and the body force. Keep in mind, double prime means per unit area, triple prime means per unit volume. And that's the dashed line over there is my control mass surface over which I am performing my integration. So I got this as CMS. Over here, it's a volume integral, so I call that CMV. Right? So this is just a symbolic way of thinking about Newton's second law. And that's a surface integral, and I said that's a volume integral. What about conservation of energy? All right, so again, various ways we can write down conservation of energy for a control mass. E is the energy of a control mass constant? The answer is no, because in general, I could have work exchange and heat exchange with the surrounding, and so the answer is no. So what about the change in energy of the control mass, right? So the energy, the total energy, if I call that E, E is the energy sitting inside this control mass. It'll increase if I add energy into it in the form of work or heat transfer. It'll decrease if I take away energy from it in the form of work or heat transfer. And that's what this expression tells me. So if I got Q and W, but I put a dot on top to indicate it's a rate quantity. So whenever I have something like a Q dot, it's per unit time, right? So it's energy. Q is energy in the form of heat transfer per unit time. And W dot N, so those things will increase the energy inside my control mass. And likewise, if I have extracting energy, then that'll reduce the energy inside my control mass, right? So this is an equation or statement for conservation of energy. Now the quantity E, just like I did for mass, or I did for momentum earlier, and I can think of rho dV as the mass, and I multiply that by little e. Little e is the energy per unit mass in that region in space. So I have a region over here where the density at this point might be rho, the energy at that point might be E, energy per unit mass, and then I'm take E, multiply that by the mass, which is rho, multiplied by dV. That gives me the total energy, little dE, if you will, and then I integrate dE to get the total energy. So E is the energy per unit mass. And E typically has several components, and for the applications in our course here, E has internal energy, which is represented by this symbol U with the tilde on top. Internal energy, again per unit mass. V squared over 2 is kinetic energy per unit mass, and G sub Gz is simply potential energy per unit mass, right? Now, the right-hand side can also be written in this manner as a sum of volume integrals and surface integrals. The volume integrals here, let me explain this one first. This FB, so the body force per unit volume acting throughout the control volume, and if I take a dot product of that with velocity, that's going to give me the work that's being done by those forces, and I integrate over the entire volume. That's going to give me the net work, the net energy that's being lost, and that's why I have the negative sign over here, and explain why that is a loss. Same idea with the surface forces. The surface forces acting on the surface lead to a surface integral, and so I have the surface force and take a dot product with the velocity at that surface of the fluid at that surface, and then multiply by the dA, area of the surface, and this product gives me the energy that might be leaving my control mass, and that's why it's the negative sign, the net energy that's leaving. And then same way, if I have heat transfer, so this is heat transfer energy per unit area, which has a double prime on it. Take it, and it's a vector quantity, so the heat transfer can be pointing in different directions. And if I take a dot product with the area, this is going to give me a scalar quantity, which is the energy, net energy leaving my control surface, and that's why I have the negative sign, since it's leaving the control surface. So this is the energy equation written in a slightly more complicated fashion, and depending on what form of problem you're working with, it may be sufficient for you to use this form of the equation, and depending on the nature of the problem, you may want to use this form of the equation, and we'll see that in this course. I've got the previous equation copied over here one more time, and I want to take a moment to explain the negative signs on those three terms on the right hand side. Let's do that. So let's imagine a surface. So we zoom in on the edge of the control mass surface, and look at this blue region. Let's say that piece of area, this indicated by this blue, has a value dA, and dA is an area vector, and so the area vector is typically the outward pointing vector, right? So the area always is a vector pointing in the direction perpendicular to that surface and pointing outwards. So dA is this little piece of area, and it's a vector quantity. Okay, and imagine this Q double prime, this is the energy transfer in the form of heat transfer per unit area, is pointing in this direction, right? If I take the dot product of those two quantities, which is this first term right here, and clearly since the angle between them is acute angle, right? This angle between these two vectors is an acute angle. The dot product, as you know from basic physics, the dot product with the cosine of the angle involved is going to be a positive quantity. And on the other hand, if Q were pointing in this direction that I've shown over here, the angle that Q makes with dA in this case is obtuse. It's a much larger angle, and so the dot product is going to be negative, right? And so this expression in some regions, some location on the surface could be positive, in some locations could be negative, and the net quantity, which is the one that's leaving the surface, is going to reduce the energy inside my control volume. My control mass, and that's why that's got the negative sign. Right. Now, having examined the basic principles for conservation of mass, Newton's second law, and now conservation of energy applied to control mass, now we're ready to turn our attention to control volumes, which is much more useful for doing fluid dynamics type. All right, so the complexity is the following. The added complexity when you talk about a control volume is that mass can go in and out. And the mass that moves in or out can also carry with it momentum. It can carry with it energy. Likewise, it can carry with it entropy if you're thinking about applying second law. So long as you keep track of it, extending these basic principles to control volumes is very doable. And that's what we will do in another video. So the basic principles themselves do not change.